So in the last video we kind of left off at just introducing the ionic lattice. It's crystalline and it's made up of negative ions surrounded by positive and positive ions surrounded by negative. You can see that in the lattice structure here. This structure, the ionic lattice, is extremely strong. So ionic compounds are always solids at room temperature with very high melting and boiling points. There's a picture of the lattice there. A kind of bigger one with all of the little individual ions in the inside. So why actually is this? It's because what is holding the ionic lattice together, so what's holding the ions together is the ionic bond. Now the ionic bond is one of the strongest bonds. That means that it takes a lot of energy to break them. It's not like molymods where we can just break it apart with our hands. That doesn't really take that much energy from us. Imagine a molymod that was stuck together so much you had to use all of the force in your arms to break it apart. That would be a bond containing much more energy. So we have to heat them to really high temperatures. The oven and the hob wouldn't be enough to melt salt. If you tried to put some salt in your oven, I do not recommend this, by the way, do not do this at home. That's your disclaimer. If you put salt in the oven or the hob, the temperatures are not going to go anywhere near the melting point of sodium chloride, which is 801. So that's the temperature that you need to take sodium chloride to in order for it to melt into a liquid. Here is just a wee diagram that I found of some salt crystals underneath the microscope, so you can see that they are in little cube structures. So we're going to have a look at electrical conductivity today. So we already know that metal elements conduct electricity, non-metal elements don't. What about ionic compounds? That's what we're going to find out in this part of the video. So, a little discussion. You can pause the video and have a wee think to yourself before you move on. So electricity is a flow of charged particles. So in order for electricity to flow, it needs to have some kind of movement of charge. It can't be stationary, it has to be able to move about. How might we test if a substance conducts electricity? And how will we know if it conducts? So what we're going to do is we're going to do some theoretical testing here of some compounds, or just the one compound, and we're going to see if we can come up with a conclusion for that. But if you want to pause and have a wee think about how we might conduct this experiment to see if they conduct electricity, how will we know if they conduct? So we're going to put our sodium chloride in a circuit. Now our circuit has to have a battery. It's got some wires, and we've got, in this instance, we have solid sodium chloride. So we're going to have some crocodile clips holding on to the solid sodium chloride, and we have a bulb. And what we're interested in is the electricity going to be able to pass through the sodium chloride, the solid sodium chloride, and light up the bulb? What do you think? The answer is no, the bulb is not going to light. Second situation, we have aqueous NaCl, which means the sodium chloride crystals have been dissolved in water. Again, it's exactly the same setup, the only difference being that instead of having crocodile clips, we have these, which are electrodes being dipped into the aqueous sodium chloride. Will the bulb light this time? Yes, it does. And lastly, the third circuit, we have molten sodium chloride. Now this is one that we obviously can't do in the lab because we need to melt it at 801 degrees. But we can certainly do a hypothetical experiment like we're doing just now. So again, we've got battery, bulb, wires, everything's all set up. We've got our electrodes dipped into the molten sodium chloride. Will the bulb light this time? Yes, it does. So, I would like you to have a wee think about this conclusion